Okay, we'll first look at question 1 of Chem Equilibrium exercise 1. Okay, so you are given this particular equilibrium reaction. So you have reactants P and Q reacting to give R and S. So you're given 4 options. So all of us should be aware that at equilibrium, the key ingredient is that the rate of the forward and backward reaction is the same. So if you just plow through all the options, option B will stand out because it reads rates of forward and backward reaction are equal. Yeah, so one of the ways where you can do MCQ is that the most obvious option, maybe you just take first, and then you slowly look through the rest and see whether they make sense or they don't make sense very quickly, of course. Yeah, so if you look at option A, it goes something like the rates of forward and backward reaction is equal to 0, so obviously it's nonsense. Yeah, because at equilibrium, or what we call dynamic equilibrium, the forward and backward reaction are still taking place. Okay, it's just that the condition is just that they happen at the same rate. Yeah, so because they happen at the same rates, the equilibrium concentration of the reactants and product remain fixed at a certain value. Okay, so we call that the equilibrium concentrations, or in terms of partial pressure, we will call that equilibrium partial pressure. Okay, so if you look at option C, the rate constant for the forward reaction equals the rate constant of the reverse reaction. This is not true. Okay, so it doesn't mean that the rate constant must be the same. Okay, so if you take the backward reaction to have the forward reaction to have the forward rate constant Kf and the backward reaction to have the backward rate constant Kb, you will notice that the values need not be the same. Okay, so one of them could be greater than the other. So in this case, it doesn't really matter. So what matters is the rates of the forward and backward reaction are the same, not the rate constant. Okay, yep. And if you look at option D, obviously this is nonsense as well, because if this is true, that means that, so what does this mean? So it means that all the equilibrium constant takes the value of 1. So obviously this is nonsense as well. Okay, so I think it's really obvious for this particular question that only option B deserve to be the correct answer to be submitted in that sense. Okay, then if you look at question 2, again, you have an equilibrium taking place between 3 gaseous molecules. So I emphasize on 3, and then eventually you end up with 1 gaseous molecule. So that's between CO, hydrogen as the reactants, and then methanol is the gaseous product. You are given the fact that the enthalpy change of the reaction is negative. Okay, so in this case, if you look at what they wanted you to do, they ask you which pair changes will definitely okay increase the amount of methanol at equilibrium. So basically they want methanol amounts to go up. Okay, so you want more methanol. Okay, and if you scrutinize the columns, you have pressure and temperature. So because you have pressure and temperature, and you notice that the combination is either decrease, 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 increase, etc., etc. So you only have 4 options. Yeah. So for this kind of question, it's actually very easy to do it by elimination. Yeah, because you just need to choose one of them, and then straight away you can eliminate 2 out. So if let's say you are very familiar, I mean just randomly, okay, very familiar with temperature factor, right? So if you take a look at the delta H, which is negative, that means there is an exothermic reaction. So for exothermic reaction overall, in the course of the reaction, heat is being evolved. So I'll put heat over here. So heat is being evolved. So that means that if I were to increase the temperature, it will favor the backward reaction, which is endothermic. Yeah, because if you recall from Le Chatelier's principle, what does it say? It says something along the line that if you apply a stress to a system at equilibrium, yeah, the position of equilibrium will shift in a direction so as to partially mitigate or partially offset the stress which you introduce. So in this case, if I were to increase the temperature, that means I increase the heat content of the system, the position of equilibrium will shift back so as to partially reduce the amount of heat being introduced. So that means that in order for me to get more methanol, I need to decrease the temperature. So in this case, I will need to choose either option A or C. Okay, then why do I decrease the temperature? Because if I decrease the temperature, the position of equilibrium will actually shift forward so as to partially offset the removal of heat which I subject the system into. So in this case, they will try to generate more heat by producing more methanol. Okay, so whatever the case is, no matter how you understand Le Chatelier's principle to be, although it's not like a perfect principle, of course there are a lot of exceptions, and it could potentially create a lot of misconception. Yeah, whatever the case is, I guess you should be able to make the correct prediction if you are able to logically deduce things from there. Okay, then what about pressure? So I think pressure wouldn't be that difficult as well, because left hand side we have 3 moles of gaseous molecules, right hand side we have 1. Yeah, so again, in order for me to get more methanol, I should be increasing the pressure so that the position of equilibrium will shift in a direction so as to produce a smaller number of moles of gaseous molecules, and in that sense it partially mitigate the increase in pressure. Yeah, so in this case I will choose option C as my answer. Yep. Okay, then we'll very quickly move on to question 3. So for question 3 begins with a recall question, which is A, what is meant by dynamic equilibrium? I think I have kind of answered it on top already. So basically that means that the key idea is you have to mention that the rates of the forward and backward reaction, okay, for a system at equilibrium is the same. Okay, so this is a very important ingredient when you need to explain what is meant by dynamic equilibrium. So the dynamic parts is related to the rates of forward and backward reaction remaining the same. And what about equilibrium? So the emphasis for equilibrium is that if you are able to take a snapshot between the equilibrium between different time frames, right, you will be able to observe that the amount of, or I mean, maybe amount is not a 100% right word, but maybe if you can detect the concentration, okay, of the reactants and products, okay, they will be actually at a fixed value, what we call equilibrium concentration. Yeah, so that actually address the equilibrium bit. Okay, so now we'll take a look at the table very quickly, table 3.1. So for table 3.1, we have table showing you how adjusting the temperature cause the Kp to increase from 10 to the power minus 10 at 298 Kelvin all the way until 10 to the power minus 5 at 1500 Kelvin. Yeah, so in this case, you will observe that as I increase the temperature, the Kp value actually increased. So from here, it is quite obvious that this is actually an endothermic reaction. So if you are if you are careful, in exams, you can simply just write delta H equals to positive over here to serve as a reminder that this is indeed an endothermic reaction, so that later on, they are probably going to ask you questions related to that. And so you can straight away tackle it without any much worry. Okay, then we take a look at the next part. Write the expression for the equilibrium constant. This is pretty straightforward. Almost equivalent to a recall, because at this stage, you should be able to easily write out the equilibrium expression. So NO squared over partial pressure of N2O2. Oh, sorry, not N2O2. Partial pressure of N2 and the partial pressure of O2. Okay, to the power of 1, you don't have to put the 1 there. Okay, deduce the sign for the enthalpy change for the forward reaction. I think earlier on I kind of mentioned it because as the temperature increase, the value of Kp actually increases. So that means that the forward reaction must be endothermic. Okay, yeah. Okay, D part 1 usually prove to be one of the more difficult kind of question that sometimes will stump students. Okay, so if you look at the question, it says something along the line that at a constant temperature, the volume of the container is actually increased to 5 dm cube. Okay, so let's take a look at the initial volume. So the initial volume is given to be 1 dm cube. Okay, so the volume actually increases. Increases from 1.0 dm cube to 5.0 dm cube, which means the volume increases by 5 times. So the question is, explain the effect this will have on the partial pressure of the individual gases. So you're asked to talk about the effect, okay, on the partial pressure of the individual gases, and then the composition of the reaction mixture. So there are two parts to the question, so we probably want to address them one by one. So before that, we will look at the equilibrium expression over here. Okay, so for this particular question, it can be difficult. It can be a little bit difficult to answer for some students, but in this scenario, it's actually very easy to answer. The reason is the number of moles of gaseous molecules actually remain constant even when you go from reactant to products. So you realize that you start off with 2 moles of gaseous molecules, you end up with 2 moles of gaseous molecules. So in this case, it's quite easy to make the prediction, to be honest. Okay, yeah, so I'll just do a quick one first, and then after that I will attempt to explain to you maybe the different scenario, and then you'll get to see how the different effect can be play out eventually. Okay, so I think first of all we'll simply use this particular equilibrium expression written over here. So I'll just use a simple approach first, maybe a slightly more qualitative approach in that sense. Okay, so we know that if you look at ideal gas, PV is actually equals to nRT. Okay, so that means that P is equals to nRT multiplied by 1 over V. Okay, so that means that the pressure is actually inversely proportional to the volume. So in that case, if you look at in the partial pressure of individual gases, if the partial pressure, if the volume increased by 5 times, you expect the partial pressure of all the gases to actually drop by 5 times. So, or you can say their partial pressure will 1/5 of their original value, in that sense, if you want to make it clearer. And then, since in this case it happens that the number of moles of gaseous molecules on both sides are the same as if you just examine the power term. So if I were to just write the 1 here, okay, there's 1. Okay, if you just write the 1, so there's 2 products, 2 moles of products, and then 1 mole of reactant each, right? Yeah. So that means that for the top portion, if you just examine it directly, it will decrease by 5 times. So that will means that I will probably put in a factor of this, and then maybe square it, and then the bottom, I'm sorry that I have to use a bit of mathematics to explain, yeah, because it might be clearer. Yeah, so you'll see how actually this allows you to understand it a little bit clearer. So that means that for this case, there is actually no effect on the overall composition. Yeah, because once the volume increased from 1.0 to 5.0, you realize that at that moment instantaneously, the QP, or what we call the equilibrium, the reaction quotient, the QP, is actually the same as KP in terms of the value. Yeah, because this term actually cancels out. Yeah, so in that sense, because the QP is the same as KP, position of equilibrium will not shift. So if the position of equilibrium don't shift, then the composition of the reaction mixture remains the same. Yeah, so for this particular case, for the production of NO from N2 and O2, increase in volume does not change any, does not have any effect on the composition of the reaction mixture. Okay, if you want a more rigorous treatment, okay, just now when I did the mathematics here, you realize that I didn't actually work out the different terms. I just roughly plug in some numbers. If you want a slightly more rigorous treatment, you can always derive the terms out from there. So let's say we know that Kp is equals to the partial pressure of NO squared over the partial pressure of N2 multiplied by the partial pressure of O2. Okay, yeah, so from here, right, we can actually take out the number of moles. Okay, so I'll just work it out for you. So we have the number of moles of NO divided by the total number of moles multiplied by the total pressure. Okay, so you'll notice that this term will be squared, and then total pressure will be squared as well. Divide by the number of moles of N2, the number of moles over the total number of moles, multiplied by the total pressure. Okay, multiplied by the number of moles of O2, divided by the total number of moles, multiplied by the total pressure, which is P. Okay, so from here you realize that the pressure term actually gets cancelled out. So the pressure terms actually gets cancelled over here, and the the total number of moles term also gets cancelled because it is squared, so it gets cancelled. So eventually you actually end up with all this taking on the original value, which means you get Kp equal a constant. So that means that for this particular system, any change in the volume will have no effect on the composition. Yeah. So yeah. So therefore, you can actually answer this question quite easily without going to the mathematics. Or if you want, you can go on and tackle the mathematics. Okay. I'm just going to illustrate something more to you, so that you get to see how this idea of reaction quotient can be applied to different systems. So let's say we talk about the Haber process, okay, which is the production of ammonia. So if you take a look at the Haber process, we have N2 gas plus 3H2 gas, and then equilibrate to give you 2 ammonia. Okay, I deliberately choose this example because in this particular example, you start off with 4 moles of gaseous molecules and you end up with 2 moles of gaseous molecules. So this is done deliberately. Okay, so if I were to write out the equilibrium expression, which is Kp, right, which is equals to the partial pressure of ammonia squared divided by the partial pressure of N2 multiplied by the partial pressure of H2 to the power of 3. Okay, so if I were to do the same thing as what I did earlier on by dissecting the terms, you realize that, okay, so I'm going to end up with the number of moles of ammonia divided by the total number of moles. Okay, so this term will be squared multiplied by the total pressure squared divided by the number of moles of N2 over the total number of moles. Okay, so if I take out the pressure term, eventually it will be P to the power of 4. Okay, so I won't bother to write it out. So number of moles of H2, number of moles of, so this is the mole fraction of hydrogen cube, and then multiply by P to the power of 4. Okay, so if I do a quick cancellation, you'll realize that this term, the numerator, total number of moles will be cancelled entirely, but for the denominator, right, I'm going to left with a squared term. So I'm going to just rearrange them. So I will end up with the number of moles of ammonia, in this case squared, divided by the number of moles of N2 multiplied by the number of moles of H2 cube. Okay, and then so in this case, I'm going to end up with something like P squared over total number of moles, 1 over. So I'm going to flip the thing over. So I'm going to get N P, sorry, this squared over P squared. Okay, so this is what I'm going to end up with. So you realize that the Kp term has a dependent factor over here. Okay, of course this is going to remain constant. Yeah. Okay, and then from here things actually gets interesting because PV is equals to nRT. All right, and therefore V is equals to RT multiplied by N over P. So therefore V is directly proportional to N over P. Yeah, so from here you realize that if I were to increase my volume, okay, this term will be bumped up. So increasing the volume will bump up this term. That means that when volume increases from 1.0 to 5.0 dm cube, so that means that the QP term being produced momentarily, right, will actually be greater than Kp. Yeah. So if Qp is greater than Kp, how do I adjust the position of equilibrium so much so that equilibrium will restore? So I think from our usual analysis in the tutorial, you realize that in order for equilibrium to be restored, right, the amount of ammonia must drop, and which means the numerator must decrease in value and the denominator must go up in value. So for that to happen, the position of equilibrium must shift to the left. Okay, so I'm not sure whether such analysis, I mean, it's okay with you, but it's pretty important to be able to analyze things from this particular perspective. Of course, if you don't want to go into the mathematics, that's perfectly fine as well. You can really simply look at the terms over here. So when you look at the terms over here, right, you realize that the top, the numerator, right, is squared, whereas the denominator is actually to the power of 4. So that means that if I were to increase the volume, right, if I were to increase the volume, although the partial pressure of the numerator decreased, okay, but the partial pressure of the denominator actually increases more. You get it? So if the partial pressure of the denominator increases more, that means that the for the reactant side, the partial pressure actually increases more than the product side. So that means that in order to restore equilibrium, I must increase the amount of products, and then of course the amount of ammonia will decrease subsequently because in order for position equilibrium to shift to the left, yeah. Of course, you can look at it from another angle. Of course, if the I think earlier on I said that if your pro, product side's partial pressure decreases less than the reactant side, yeah, that means that the number below will decreases more, and then your moment, the QP being generated momentarily, right, will actually be bigger than KP. So when that happens, in order to restore equilibrium, position equilibrium will have to shift to the left. Yeah, because why shift to the left? Because my denominator must go up in value, my numerator must go down in value. Yeah. So no matter how you analyze it, actually all road leads to Rome. You will be able to end up with the correct conclusion, but just ensure that you analyze it in the correct manner. Okay, we can also look at another system where in that case it's actually the other way around. So that is like N2O4 equilibrate to give me 2NO2. Yeah, you realize just now it was reactant heavy product light. Now it's product light reactant heavy. So I have two moles of products. Okay, so you can use the same logic. Kp is equals to the partial pressure NO2 squared divided by the partial pressure N2O4. Then again, you after you dissect the terms, you should be able to get NO2 squared divided by the number of moles of N2O4, and then multiply by P over R. Oh, sorry, P over the total number of moles. Okay, so we use the same logic, PV, and of course this is the dependent factor. Okay, so we have PV equals to nRT, and then after that V will therefore be nRT over P. So in this case, the relationship is inverse. What does inverse means? That means that if my volume increase from 1.0 to 5.0 dm cube, yeah, that means that this particular term, right, will actually decrease in value. Okay, so when this particular term actually decrease in value, that means that momentarily the QP is less than KP. Yeah, so in order for equilibrium to be restored, the numerator value must go up and the denominator value must go down. Yeah, so in this case, my position of equilibrium will actually shift to the right. Yeah, so in order to restore the equilibrium. Yeah, so it's the same logic as before, except that in this case, I have more product than reactant, whereas in the earlier case, I have more reactant than products. Yeah, so the examples in the in-class exercise 1, right, is actually the easiest kind of examples because the number of moles of reactants and products are actually the same. So it's actually quite easy to analyze. So, okay, yeah. And of course, predict how the value of Kp will change. I think this can be answered definitely very easily because Kp is only a temperature dependent variable. So this is only dependent on temperature. So in this case, no matter whether you up the pressure, you down the volume, you add reactant or what, it won't affect the value of Kp because whatever stress you introduce to the system, the position of equilibrium will adjust in a direction or shift in direction so as to mitigate the the stress being introduced. Okay, and then for part E, the value of Kp does not change when a catalyst is added. Why is that the case? So I think we mentioned a few times and also in the videos on the equilibrium topic that the presence of the catalyst merely allows the equilibrium to be established more quickly. How does it allow equilibrium to be established more quickly? It actually provides an alternative pathway, okay, for the reaction to undergo. Yeah, so the alternative pathway actually have a lower activation energy, and because of the lower activation barrier, equilibrium can be established at a faster rate. Yeah, so the presence of the catalyst does increase the rate of both the forward and backward reaction. Okay, so I think that is also something that you need to be aware of. Yeah, I think that's about it. Watch out for the next video on in class. It's nice too.